Hello guys, um, yeah, this is me. I'm just working on section 13.2. This is gonna be the lesson for section 13.2 and 13.3. This is basically a continuation of section 13.1, which talks about solving systems of equations using the graphs or graphing the system of equations. And in section 13.2, though, we will solve systems of equations by using the substitution method, and either the substitution method or the elimination method. And I will tell you what those look like. But first, we need to remember that and let me make the camera available here, projector, Elmo, as I want to call it. Oh, okay. Hold on. First, we need to remember that. Let me close that. There you go. First, we need to remember that well, we used to solve for equations like with one variable, x, like x plus 1 equals 3, by either using the addition principle or the multiplication principle. For example, here we could subtract -1 from both sides, and this cancels out. Rewrite my x, that's equals 3 minus 1 is 2, positive 2. So my x is the value of 2, and we're done. And we are mathematically correct. We have proven that again and again. So we know that this works. The addition and the multiplication principles work, and it makes the equation true. Let me show you a different example here with variables. For example, 6 plus 1 equals 7. Well, if I subtract 1 from both sides, well, I get different equations. The equations are not, the equation is not 7 equals 7 anymore. It is 6 equals 6. So by subtracting -1 from both sides of the equal sign there, all I did was keep the equation balanced. So that's what this does basically. Some teachers call it keeping the equation balanced. That's what I would call it too. And in this case, it brings the equations from 7 equals 7 to 6 equals 6. However, we know that these equations are true, therefore this is mathematically correct. This process is mathematically correct, and I'm able to see it here. I'm not able to see it here. However, this is what we're doing here. We are changing the equations to look like this. A little bit different. Well, they are different, and the process we used is the same as this one. Therefore, we know that mathematically this is correct. This is correct. Okay, so that's what happens when you solve for equations with one variable. In the previous section, 30.1, we talked about solving systems of equations. Systems of equations. And that means we're going to be working with more than one equation at a time. And in this case, just two. But you could work with more than that. And they also have two different variables in them, because and let me show you what it looks like. A system of equations with two variables. And this is coming right out of the book, so you don't have to write most of this down. Just know that it's in there, to make it easier on you. I'm just writing the example 3 in page 181, right out of the book. So that's x minus 2y equals 6, and 3x plus 2y equals 4. That's what it looks like. System of equations. We have at least two equations, and we have two variables. I mean, we could have one variable, that's fine. However, just remember that you already know how to solve for x, like when you only have one variable in the equation. So that would be simple enough to solve. In this case, we have two variables, and that's a little bit more difficult. Just think about it. If you have an equation that looks like that, you just wouldn't be able to solve it just by using one equation. You just can't. Okay? You'll be going back and forth, solving from x to y, y to x, and you wouldn't be able to solve that equation. You would get zeros on both sides and all kinds of different things, but you would never be able to solve for x and or y. Therefore, we need two equations in order for us to be able to solve for two different variables. All right. So, and then the first thing we need to get very, very clear is that when we have two systems of equations, and I have my notes here, let me pull them up close to me. When we have two systems of equations, we can do different things. Let me start by writing a different system of equations. So let me forget about this for now, and let me write an example from my own. And because we need to get this concept straight first. Okay, so I'm gonna write the equation 2 plus 2y equals 8, and the equation 3x, oh, my mistake, that's x here, x, and 3x, because this is a system of equations, remember, minus 4y, and you don't have to write this down. This is just my example trying to show you the transition from solving one variable to solving two variables at a time. All right, and that's nearly 6. All right, so now I have my own system of equations here. And in this case, I have decided that x equals 2 and y equals 3. Okay, just a random. That's what I chose, because you substitute them in here. So your x, you substitute the 2 for your x, and this 3 for your y, you will get an 8 on this side. Oops, 2 times 3, that's 3. 2 times 3 is 6, plus 2 is 8. Okay, and same thing here. If I substitute 2 for the x and 3 for the y, that's equals -6, because 3 times 2 is 1. I'm going to write that down there. And -12 here, and 6. 6 minus 12 is -6. So I knew that was going to work. Those two values were going to work, and they do. They solve the system equations. But the first thing we need to notice is that, or what I wanted you to notice is that these two are solutions of these equations because they are true. See, when you substitute the values, they are true. They give you true equations. Therefore, this system of equations is true, and your solution is x, well, the order pair 2, yeah, more specifically order pair 2, 3. All right, and then I'm just gonna write a line just to separate those two. That's this equation and this equation. All right, and from here, if I told you that we could mix up these two equations, would you believe me? Well, you probably wouldn't. You probably believe me that I could mix this equation with this equation, yeah, or vice versa. Because it's not very intuitive. It just doesn't seem correct. But let me show you. Let me try to show you that it can be done. Okay, so let's say, well, I'll tell you what. Let me use this equation, these two equations, in this form and this form first, so you can see it better, because those are already in constant form. They have constants as the answer and not variables, so you can see it better. Okay, so let's say I use this equation, write it down over here, 8 equals 8, and then subtract, and then basically subtract -6, or write this number here and this number here, -6, and I have mixed them together. I have mixed these two equations together, or in other words, these two equations together, except for they were in a constant form here. All right, and let me show you why this is mathematically correct. Okay, so if I add them up, 96 plus 8 is 2. 8 minus 6 is 2. So this equation is also true. Therefore, this process was mathematically correct. Okay, so yes, we can mix up equations in whenever you have them as a system of equations. Okay, we already knew that this was a system of equations. Okay, so in other words, these two oops, hold on, there. And that's that's one of the reasons we can mix them up and still be okay. But you actually can mix up any equations, even if you don't have them as a system of equations. In this case, a system of equations, when you have a system of equations, that only tells you that your x's, your x values will be the same, your y values will be the same from both equations. Let me see if I can word it differently. If I give it, if I give this x a value 2, then I should give this x also a value 2, because that's what a system equation is. Whenever you have two equations and the variables are the same, the author is telling you that that value is the same for both equations. Same for this y. That y should be, the value for that y should be the same in both equations whenever you have a system of equations. What's the difference now? Well, the difference now is that back whenever you were solving for x and y, and you x in one problem gave you some value, and the x in a different problem gave you a different value. Well, that's because you were talking about two different problems. See? In this case, though, you're talking about a system of equations. System of equations that both of them are included in the same problem. Okay, and they are telling you that it is a system of equations. Okay, therefore, you need to assume that the x values are exactly the same, the y values are exactly the same. If they weren't, well, they would tell you that by writing a different variable here and a different variable here. However, they didn't. They used x again and y again here. Therefore, this x value is the same for this one, and this y value is the same for this one. Okay, so that's a big difference there, big transition there, from working with one variable to working with two variables in system of equations, in system of equation form. Okay, and from here, I was talking about trying to mix up these two equations, which is what I did here, except for I use the constants from both equations, the constant form for both equations, combine them together, and mathematically it is okay. I mean, there's no value to it, but I was showing you that you can mix them up. Okay, so that's what I was trying to prove, that yeah, you can actually mix them up, and it's okay. Mathematically it will be okay. Again, if you still don't believe me, let me show you. Well, let me rewrite my equation here. Well, one equation, a different equation. Remember that when we solved for x, all we did was subtract -1 from both sides. Just cancels out. X equals 2. Okay. And what does it look like whenever you have constants? Well, it looks like this again. I'm just rewriting from the top of the page, I think, and that's -1 minus 1, and this comes out. Rewrite you 6, -1, 7 minus 1 is 6. So my equation is still true. This was still true. My equation here is still true. Okay. I just wrote the equations differently. This I have constants. In this equation I have variables. But just so you can see it better, here with constants, working in with constants, you can see that your expression looks different, and because it is different. However, it is true, therefore it's mathematically correct. All you did was balance it by subtracting from both sides of the equal sign. That's basically what you did there. That's basically what you did here. You balanced it. You just didn't see it. You can't really see it here. You can see it better here because I can see that 7 equals 7 here and 6 equals 6 here in this equation. Okay. So so that's exactly what we did. Just balance it. Isn't that the same thing I did here? Subtracted 6 from this side, subtracted 6 from this side. That's exactly what I did. I balanced the equation. And since it is mathematically correct to do it here, therefore must be mathematically correct to do it here, right? Yes, it is. And in this case, it just so happens that this negative 6 is the same as this negative 6 from this equation, and this negative 6 is the same as this the negative 6 from this equation. Okay, so yeah, you actually can mix them up. So that's my second proof there. You can actually mix up the equations and be mathematically correct. So this is good. This is good. You can do it. Okay. And I will go even further now, because now that I know that I can mix them up by using the constants here, the constants version of these equations with variables. Now I want to go ahead and use these equations in variable form and mix them together. Okay, so I have an x from the first equation, and then a positive 3x, and from the second equation here, and then a positive 2y from the first equation, and then a negative 4y from the second equation. And you still don't have to write anything down yet, because I'm just giving you this example here. And then I have an 8 from the first equation and a negative 6 from the second equation. Alright, now we have them all combined in one single equation, and we already know that that's mathematically correct. Okay, the only difference here is that we have I'm writing my variables here. Alright, so what are the rules here? Well, we combine like terms. In this case, we have an x here, 3 x's here, combined together gives me 4 x's. I have 2 x's here and negative 4 x's here. That will give me 2y, negative 2y. And on the other side of the equal sign, I have x minus 6 is 2. Alright, from here, since I know that a solution for these two equations is the order pair 2 and 3, well, I can substitute 2 for x here and 3 for y here, and then just multiply 4 times 2, that's 8, and 2 times 2 is 6, equals 2. 8 minus 6 is 2, and the equation is still balanced. So yes, it worked. Mixing them up works. Okay, mixing up the two equations in the system of equation works. And we already knew that. See, from here, get the equation balance. So we already knew that. We already knew it worked. The only difference was we worked it out with constants here. Here we worked it out with variables. Okay, so it does work. It does work. And that should be the introduction to this section. What did we learn? Well, the transition is that before we used to work with equations with one variable only, and it was simple, simple enough to solve for that variable. You just also isolated the variable, and you will have your value of x. Now we are working with systems of equations. Oh, and before we went from problem to problem, and your x would have been different. The value for your x, for your variable, would be different. Would have been different. Okay. And whenever you have a system of equations, the value for your x is not different. The value for your x or your variables are the same. While the values for your y's are always the same. Okay. Whenever you are working with system of equations, okay? Because this is just one problem. The whole thing is just one problem. Okay. And that's one way of thinking about it. What else? We learned that we could mix up these two equations together, and mathematically it still would be okay. Okay. I proved it twice. I believe I proved it 3 times. Okay. Or yeah, 3 different ways. But it does work. Mixing them up does work. And I had to bring that up because that's what's gonna make a transition and from solving from one variable to solving 2 variables in systems of equations. Okay, and that's our introduction to section 13.2, because section 13.2 talks about the substitution method. And this is where I need a new page, because now this you can write down and have it as your notes. And I'm just gonna write down the section of that chapter, which is chapter 13.2. The section will be 13.2, and we are solving systems of equations in 2 variables. I'm just gonna open up a parenthesis here. There you go. You don't have to write that down, but that's what it is. That's basically why we're doing it, and I show you that, yeah, if you were solving for x, you could do it with just one equation. However, if you have 2 variables, you cannot. You just can't do it with one variable. I mean, one equation. You can solve for both variables just with one equation. No, can't do it. That's why we need a system of equations. That means at least 2 equations. All right. And then for the example, again, the example is in page 281, and it comes from section B, or objective B, actually. Objective B, we skip A because A is essentially section B, except for you have you need to solve for x. In section B, we need to solve for x. In section A, the equations, at least one of the questions is already solved for x, has already been solved for x. So in section B, we need to solve for x, and we are using again the substitution method. Substitution using using substitution method. All right, and then the example is example number 3, and the problem is x minus 2y equals 6, and I'm getting it right out of the book, so you don't have to write most of this stuff down. It's gonna be in there. If you want, you can write down the steps, that's fine. Plus 2y equals 4, and that's the system of equations. Okay, by substitution of what? And this is one way of memorizing this name here. Well, we can solve one equation for x and then substitute that value into the other equation. That's where the name comes from. Okay, so in this case I can solve the first equation. It doesn't make a difference with which equation you solve first, and if you solve x first or y, it doesn't make a difference. Just go ahead and start with one. The one that looks easier, this one looks easier because it has a factor of 1. So all I have to do here is, let me rewrite it. X minus 2y equals 6. All I have to do here is add 2y both sides. 2y. This cancels, and I have 2y on 2y plus 6 on the other side, and now I have x equals 2y plus 6. And didn't we just say that your x's should be the same in both equations? Well, taking that knowledge, we can substitute this value into this equation, so into the other equation. Okay, not into the same equation. We cannot do that. Not when we're solving for a variable, and we have a variable on the other side, we cannot use that value into the same equation. No, that would be, it would just draw you in circles, because you would end up with your y, or getting rid of the variables, and all kinds of weird things will happen. Like, you will never be able to solve variables using the same equation. So you have to use the other one. Okay, in this case the other one is 3x. In this case x is 2, y plus 6, and the rest of that is plus 2y. And since x was a factor of 3, I need to draw parentheses around this expression, okay, because that's a factor of 3. And then just rewrite plus 2y plus 4. All right, and then just, if you notice, this is a y variable, this is another y variable. Now we have y variables in one equation. So now this I can solve for y. See? And this is mathematically still correct. Yeah. What I do is, well, follow the order operation. The order operation calls for multiplication first. I have multiplication here, however, I can't do anything to that. I have multiplication here between the parentheses and the 3. So I do that by distributing the 3 inside the parentheses. 3 times 2 is 6, 6y. 3 times 6 is 18, and then just rewrite 2y equals 4. Now I'm here. Now I can see that I can combine like terms. See this y? I have 6y here, 6y is here, 6 and 2 here. Add them up. I get 8y, and then just rewrite the 18 there equals 4. 18 needs to be moved to the other side by using the addition principle. That's what I do. Add them up. This cancels. I end up with 8y on one side equals 4 minus 18 is negative 14, and then y and this will by itself, so I use the multiplication principle by dividing by 8. This simplifies to 7, negative 7 over 4. Yeah, just divide by 2. By 2, 7 over 4. And yeah, that's the correct answer according to the book. So we have that our y in these two equations. So these two y's are the same as this, have the same value as this. Okay. And since we already know that, now we can substitute into any of these two equations, okay, and solve for x. Okay. Now we can use this value into any of the two equations, because now you don't have any variables on the other side. Okay. Back here, we can use x equals 2y plus 6 into the same equation, because we had a variable on the other side too. So we had two variables. Here we can use this y in any of the two equations, because we don't have a variable over here on the other side. We don't have two variables, we only have one. So now we can use any of the two variables there. I'm going to use the first one because it looks easier. So the equation is x minus 2y, hold on, and equals 6. Okay, I just wrote down the equation, and I will substitute now. X minus 2 times negative 7 over 4 equals 6. Alright, so if I multiply here, well, I'm basically can basically divide by 2 and simplify before I multiply. That will leave me with well, negative and negative. When you multiply, it gives you a positive. So x, you end up with x plus, and that's 2 there, because I divided by 2 to simplify this 2, and the answer will be plus 7x equals 6 there. And then just continue, continue solving for x, isolate the variable by using the addition principle. 7 over 2 on both sides. This cancels. I have x on one side, and here I have 6 minus 7 over 2. 6 minus 7 over 2. Well, what is my what is the rule there for subtracting fractions? I'm just gonna rewrite it here. Well, we need a common denominator or a least common multiple. In this case, it's 2. It's easy to see because it's only 2 and 1 there. So 2 will be my denominator. I raise this 1 by a factor of 2. Therefore, I need to raise this 6 by factor of 2 also. I did not raise this denominator, so I just rewrite my other denominator, my numerator. In this case, I do have common denominators, so I just rewrite that 2 there and subtract 12 minus 7 is 5. So my x equals 5 over 2. According to this, and according to the book, yes, it is correct. So my x equals 5 over 2. So I'm just going to rewrite that x values, x value and y value up here as an order pair. As x, oh, new y value there. X and y, x was 5 over 2. And my y value was negative 7 over 4. And yeah, you are sometimes you're gonna get fractions as the answer. That's okay, because we already solved for x and y for 2 variables with a system of equations. Okay, and that's the way you do it if you haven't solved for x yet. Okay, if you have already solved for x, then it's not gonna matter. Okay, and that is example 3 in page 981. I said. Now we're moving on to example 4 in section hold on.